Right, so sections 5.2 and 5.3 dealing with our power functions, polynomials, and their graphs. Our objectives in this section are being able to identify power functions and their end behaviors, being able to identify polynomial functions, identify zeros and their multiplicities, which you have a brief understanding of from that previous lesson that we just went over, and then graphing / sketching out polynomial functions by utilizing the zeros, their multiplicities, where they bounce off your x-axis, as well as your knowledge of end behavior. And then finally, the last objective, which is an important one, especially if you are going to be taking future math courses, being able to use your intermediate value theorem for polynomial functions. So we have a definition, power function. Maybe I'll have one of you guys read this for me. Anyone want to volunteer?
A power function that can be represented in the form f of x equals kx to the power, where k and p are real numbers, and k is known as a coefficient.
Thank you. Yeah. And again, that k is sort of like the a when it comes to quadratics. If the k is negative, then the whole entire function is going to be reflected. It's going to be upside down. And we'll really be honing in on this when we're looking at the relationships of even degree polynomials versus odd degree polynomials and their end behaviors, dealing with reflections and stuff. Again, even degree and odd degree polynomials, very different from even and odd functions, which is what we defined, if not yesterday, then the day before. But I'll repeat that once we get to that point in the lesson. All right, so we are identifying power functions here, and we're given a whole list of some famous functions that you should know graphically. And so again, what is our format for our power function? We want f of x to be some constant. Constant could be 1, times x to the p power. All right. So maybe I'll have some students read these. Getting tired of my voice. I'll have someone do orange and then another person do blue. Anyone for orange? Yeah, go for it.
The behavior of the graph of function is as the input values get very small, x to the and get very large, x to infinity is referred to as the end behavior of the function.
Good. Blue? Yeah.
The table on the next slide shows the end behavior of power function in the form of f of x equals kx power of n, where n is a non-negative
Integer. Yep.
Depending on the power and the constant.
Good. Non-negative is just a fancy way of saying it's n is greater than or equal to 0. Which actually, if that's the case, then technically a constant function would be considered a power function. So Ariana, right again. So yeah, let's change that. If it just said n can't be negative, then that's where our p would have to just be greater than. No, then it would be, yeah, non-negatives greater than or equal to 0. It's all positive and 0. So if p is 0, then yeah, that shoots to 1. Okay. So this last part over here is just when you're given a power function, how do we identify the end behavior? And so I verbally spoke about this during the objectives. But essentially, we want to look at even degree and odd degree polynomials. And then obviously, if our k value is negative, then reflections will take place and we'll go from there. But there is a pattern when it comes to even and odd degree polynomials and their end behaviors. So we'll be looking at that now. And so anytime you're dealing with even power or even degree polynomials that have a k value that's positive, then again, the easiest example you want to look at is x squared. Have this U-shaped parabola, and then from there, it's very straightforward to identify what your end behaviors are. You just look at your graph, and as x approaches negative infinity, what's happening to your y values? They're approaching positive infinity. And so that's where you get this first part here, right? As x goes to negative infinity, our y shoots to positive infinity. And then if you look on the right-hand side, as x goes to positive infinity, y also continues to shoot to positive infinity, which is that second part. As x goes to positive infinity, y also goes to positive infinity. Obviously, if your k is now negative, then it's just going to be upside down. And so when your k is negative, x shooting to negative infinity, your y is now negative infinity. And then as x shoots to positive infinity, your y is once again negative infinity. We look at this solely from x squared because that's the easiest one to visualize. But this pattern works for any even degree polynomial. So that's why we call it even power. We have works for all even degree polynomials. Whereas the odd degree, the most famous one you want to be looking at is our cubic function. So our x to the third. And then you once again just look at the graph. When x goes to negative infinity, our y shoots to negative infinity. But when x goes to positive infinity, our y shoots to positive infinity, which is what we have down over here. This is when our k, once again, is positive. That leading coefficient's positive. Now, if it's negative, then it's just flipped. You're reflecting your entire function across your x-axis. So now you're looking at this cool-looking function, whereas x is going to negative infinity, our y shoots to positive infinity, and then when x goes to positive infinity, our y shoots to negative infinity. Right. Once again, this works for all odd degree polynomials. So anything to the 7th power or the 23rd power, so on and so forth. Odd degree is not the same as odd function. Odd function, we use the definition f of negative x is equal to negative f of x. Even degree is not the same as even function. Your even function definition is f of negative x equals f of x. So I'm going to actually make a slide on that because I do find that to be a very common mistake. Odd and even degree polynomials are not the same as odd and even functions. So for this, we look at end behavior patterns. And then with this, we look at our definitions. Questions at all? Okay. So let's take a look at example 2. We have find the end behavior of the graphs x to the 8th and then x to the 9th. So x to the 8th is even degree. Just compare it to our x squared, which is also even degree. And because our k value is 1, it is positive. So no reflection is needed. And so it's the same as our x squared. As x goes to positive infinity, our y shoots up to positive infinity. As x goes to negative infinity, our y still shoots up at positive infinity. That's it. You know the power is even and there is no negative, then just look at x squared.
So basically, one follow another.
Yeah. Even numbers follow even numbers. Yeah. Odd numbers follow odd numbers. The only thing that you have to be mindful of is that k. Is it negative or is it positive? Because if it's negative, then the whole thing is reflected and you just want to look at it visually. Right? And then we have x or negative x to the 9th, which is an odd degree polynomial. But in this case, our k is equal to -1, which is less than 0, so it's opposite. So our x to the third is usually like this, but our negative x to the third is flipped. And so we're looking at something like this. That's the one that we're gonna hone in on. And then you just look at the graph to figure out what your end behaviors are. As x goes to positive infinity, we have y shoots to negative infinity. And then as x goes to negative infinity, we have y shoots to positive infinity. That's it. We're done.
So it's like when it's positive, they're going to be the same in the first and second quadrant, and when it's negative, they're going to be reflected in the top and the bottom.
Doesn't have to be first and second quadrant, but when it is when they're even degrees, your y's are going in the same direction, whether it's up or down. And then when it's odd degrees, your y's are going in opposite directions. And depending on whether it's negative or not, it's either going to go opposite directions this way or opposite directions that way.
Like reflection, but
Exactly. Yeah, you got it. All right. All right. So we're on the second objective, which is being able to identify polynomial functions. And maybe I'll have someone read the definition of a polynomial function. Just have you guys read up to the yellow part. Yeah, go for it, Valerie.
Polynomial functions, let them be a non-negative
Integer.
A polynomial function of degree n is a function that can be written in the form p times x equal an over x.
Yeah, it's a sub n, x to the n, and then plus a sub n minus 1 to the times x to the n minus 1 plus dot dot dot, plus a sub 2 x squared plus a sub 1 x plus your constant. So this is just the general format of representing all of the polynomials in the mathematical world. And then we have some more vocabulary words. We have degree, we have leading term, and then we have leading coefficient. And so the degree, to determine the degree of a polynomial, you always want to look at its highest power. So the highest exponent, if it's 5, then we have a 5th degree polynomial. If it's 3, then we have a 3rd degree polynomial, also known as a cubic function. If we have 2, then we have a quadratic function. Leading term is the term that contains that highest power. So if it's 5x to the 5th, that 5 is the highest exponent, then 5x to the 5th is your leading term. Whereas leading coefficient is just the coefficient of that leading term. So 5x to the 5th, 5 would be your leading coefficient. And so this is more of a visual. Your leading term is always going to be that highest degree, where we have n in that general case, and that leading coefficient is that a sub n. Yeah. So in these 3 function examples, f of x, g of t, and h of p, we want to identify the degree, the leading term and the leading coefficient. So I think what I'll do is I'll write out degree leading term and then leading coefficient. And then create maybe like a chart. So we have f of x, we have g of t, and then we have h of p. So degree of f of x is what? What's our highest degree? 3. What's our leading term? Term is, remember, separated by the plus or minus signs. So we have 3 terms here, but we're just asked for the leading term, which is negative 4x to the third. And then our leading coefficient is negative, what's the coefficient in front of negative 4x to the third? It's negative 4. All right, g of t, what's our highest degree? 5. 5, right? Because it's the exponent, the little numbers. The exponent here is just 1. The leading term is 5t to the 5th. And then our leading coefficient is 5. What about h of p? What's our highest degree? 3. What is our leading term? Be careful, it's always the highest degree. That's the term, so negative p to the third. And then our leading coefficient is, yeah. Have 2 students read this. Someone read the purple, and then someone read, I don't know, green. Who would like to read purple? Ariana.
Knowing the degree of a polynomial function used to help us predict its end behavior. To determine its end behavior, look at the leading term of the polynomial function. Because the power of the leading term is the highest, that term will grow significantly faster than the other terms as x gets very large, very small, so the table will dominate the graph.
Thank you. And then green, Alexandra.
Polynomial behavior of the polynomial function and behavior of the power function consisting of leads.
Good. Thank you. Right, so end behavior of polynomial functions. We're getting quite good at this, especially after that whole lesson on our odd degree and even degree patterns. But essentially, once you know what the visual looks like, then you're just looking at, okay, what happens to your x as it approaches infinity, and then at the same time, what happens to your y versus what happens while your x is approaching negative infinity, what happens to your y, and so on and so forth. That's where end behavior comes into play. So now we arrive at our example 4, where we want to identify end behavior and degree of our polynomial function. So we're given the function f of x is equal to negative 3x squared, in parentheses, x minus 1, x plus 4. We want to express the function as a polynomial in general form, so we're going to end up using some FOIL and distribution. And then we want to determine the leading term, degree, and end behavior. So I'm first going to FOIL out those two binomials in order to get x squared plus 3x minus 4. And then I'm going to utilize distributive property. So then I end up with negative 3x to the 4th minus 9x to the 3rd plus 12x squared. And so from what we have in red here, now we can very clearly identify that our leading term is our highest degree, which is our 4th power, so negative 3x to the 4th. And our degree, we're looking at a quartic function of 4th degree. And then finally, we have our end behavior. Well, it's an even degree, so we think of our x squared, but because it's negative 3, we want to look at our negative x squared in order to determine your end behaviors. So from here, we have as x goes to negative infinity, our y shoots down to negative infinity. And then as x goes to positive infinity, our y continues to shoot down to negative infinity. And we're done. Up for a second. Right. So our next slide is talking about our local behavior of polynomial functions. And I guess I'll read this slide for you guys. So we have, in addition to the end behavior of polynomial functions, we're also interested in what happens in the middle of the function, aka some turning points. So in particular, we're interested in locations where graph behavior changes from increasing to decreasing or decreasing to increasing. So what are these known as? These are known as turning points of polynomial functions. And then it's also important to understand our intercepts, especially our x-intercepts, because that's where your graph is going from negative to positive in the y direction, or vice versa, positive to negative. And it's sort of like the preview into intermediate value theorem, which is a very important theorem with identifying potential roots for your function. Turning point of a graph, I subtly stated it, but it's just when you're going from increasing to decreasing or vice versa, decreasing to increasing. So with example 5, we're given this polynomial. I'll write it a little larger so you could see it a bit more clearly. X minus 2 in parentheses x plus 1 in parentheses x minus 4. And we want to determine our x and y intercepts. So it's quite clear to identify your x-intercepts here since it's already in factored form. So in ascending order, we have -1, we have +2, and we have +4 are x-intercepts. Now, in terms of y-intercepts is always quite straightforward because it's just defined when x is equal to 0. So what do? We just plug in 0 wherever we see x's. And so essentially we're taking the product of -2, +1, and -4, and that will yield us 8 to be our y-intercept, which in coordinate form, it's 0, 8. And that's it. Just wanted to calculate the intercepts. Right, some more definitions when we're looking at characteristics of polynomial functions. And so we have a function is continuous and smooth. And what does continuous mean? Maybe I'll use different colors for each one. Continuous is if you were to put down your pencil and just continue to draw on your piece of paper, there would be no breaks in the graph. The second you lift up your pen or your pencil, then you have a break and the function is no longer continuous. So all continuous functions have no breaks and it can be drawn without lifting the pen from your paper. Whereas smooth just has no sharp corners, so there's no cusps that are happening. Round curves are acceptable, points are not. The turning points of the graph of a polynomial function must always occur at rounded curves, so no cusps. And then finally, we have a polynomial function of degree n will have at most n x-intercepts and n minus 1 turning points. The n minus 1 turning points also really helps with determining how many humps you have. So for example, if you have a quadratic function x squared, your n value is 2 here. And so n minus 1 is 2 minus 1, which is 1. And that tells us that we have 1 hump or bump, whatever you want to call it, going on. And that's correct, right? Quadratic functions have that 1 bump. But if you were dealing with maybe a quartic function, say x to the 4th, obviously would have to be a variation of x to the 4th with distinct roots, but you end up having 2 humps, 1, 2, or sorry, 3 humps, 1, 2, 3, because your n is 4, and so n minus 1 is 4 minus 1, which gives you 3. So the number of turning points is equal to the number of humps that's being represented. We're on objective 3, which is identifying zeros and their multiplicities. And so if p is a polynomial function, then c is called a zero of p if p of 0 or p of c is equal to 0. And so we'll really be honing in on this, utilizing our zero product property, which we have down below over here, but also when we're looking at the remainder theorem as well as the factor theorem. And this is just sort of the step-by-step procedure with finding zeros of polynomial functions. Okay. Example 6, we want to find the zeros of this polynomial. We're given h of x is equal to x minus 2 in parentheses squared, close parentheses, 2x plus 3. So zeros is just a synonym for x-intercepts, also known as roots. All we have to do is, it's already factored, so we're very lucky. We just have to set each of the parentheses equal to 0. So we have a multiplicity of 2 taking place here. Over here, we have x is equal to 2 twice. And then with the 2x plus 3, when we set that equal to 0, we end up getting that x is equal to negative 3 over 2. So all of our zeros are x equals negative 3 over 2 and 2, and I'll put in parentheses with a multiplicity of 2. So at 2, you're going to have a little bounce that occurs off of the x-axis. That's it. Any questions on this one? I believe we have 5 more examples from this section, and we should be done. Multiplicity. This is the formal definition. When you're dealing with a factor where the exponent is greater than 1, so whether this p-value is 2, 3, 4, 5, that p determines what your multiplicity is for that 0. So if it's raised to the 5th power, then we have a multiplicity of 5. If h was, I don't know, 8, that would say at the value 8, we have a multiplicity of 5. 8 is being repeated 5 times. And then this second part is stating that the function will touch the x-axis at the zeros with even multiplicities. So if you have a multiplicity of 2, you'll really emphasize that bounce off the x-axis. But if you have a multiplicity of 4, it will also hit the x-axis. It won't be quite of like a bounce, a basketball bounce. It'll be sort of like a little bit longer in terms of a horizontal line. And I'll show you maybe. So x squared, you very can clearly see that bounce, but x to the 4th, it's more, it keeps getting flatter at the bounce. It's like a long, prolonged bounce. And then if you're looking at like x to the, I don't know, 12th, it'll be even more. I'm really accenting it so you see the visual, but yeah. And then that last part is when we're looking at odd multiplicities. If you have odd multiplicities, then it's going to shoot through the x-axis. So think of like x to the 3rd power, right? We have an odd multiplicity at 0. We have 3 roots of 0. Notice how it crosses over. And then the sum of the multiplicities is the degree of the polynomial function, which is kind of cool. And we'll show that when we start sketching out these a bit more. Right, example 7. We want to use the graph below. They even tell us in the problem that it has a degree of 6. And we just want to identify the zeros of their functions and their possible multiplicities. So zeros are quite straightforward. You literally just look at your x-intercepts. And so we have -3, it's bouncing off. We have at -1, it shoots straight through. And then we have at 4, it also shoots straight through, but the direction is changed. So this sort of looks like an odd degree, whereas this one just goes straight through. There's no turning point. And this one just bounces off. So where do you think the multiplicities are taking place? Well, first let's identify the zeros. So our zeros are the following. We have x is equal to -3, x equals -1, and x is equal to 4. Now, in terms of multiplicities, again, think we have a polynomial function of degree 6. So right now we have just 3 zeros. We're missing 3. So where do you think a multiplicity lies? Do you think -3 is repeated? Right? It bounces off the x-axis, right? So we have a multiplicity of 2 here. Okay, so now we're up to 4. What about this one over here? Is that repeated? Yeah, right? What multiplicity do you think? No, it only bounces off the x-axis if it's even. So remember over here, anytime it's even multiplicities, it's going to touch the x-axis at the zeros. Whereas if it's odd, and you're dealing with multiplicities, it's going to cross straight through the x-axis. And a good example of the odd one is x to the third. Yeah. And so you can kind of really see that one right here, right? So, and we're dealing with cubic, so we have a multiplicity of 3 here. Whereas this one just shoots straight through. If there's no turning point that's occurring, meaning this goes from increasing and then it stops right here, and then we have another increasing, whereas this is just decreasing straight on through, then you don't have, this is just a multiplicity of 1. It's not being repeated. And so now does this add up? We have 1, 2, 3, 4, 5, 6. If you wanted to write it out repeated, then it would be x is equal to -3, -3, -1, 4, 4, 4. And then we're done. Any questions? All right. Let's continue. So this is graphing polynomial functions, and we're bringing back our knowledge of even and odd functions, which once again is not the same as even and odd degrees. Even functions is when we have f of -x is equal to the original function, whereas an odd function, we have f of -x is equal to negative f of x. And so we utilize these definitions in order to check for symmetry and reflections about the x-axis as well as the y-axis. And then we use the multiplicities to determine the zeros, the x-intercepts, and if there's any bouncing or straighting through taking place, as well as determining end behaviors. So when we put all of this together, then we can really get a good sketch of these types of functions. And then right down here is sort of like the step-by-step procedure. You want to factor to find all the real zeros, aka your x-intercepts, and then you want to make a table in order to include test points to determine where the graph is going to be above or below your x-axis. Obviously, also include your y-intercept. That's a very easy point to just add in. And then your end behaviors are straightforward based off of your patterns for even and odd degrees. And then once you have all of those facts, then you can really create your sketch of a cubic function or a quartic function or a 6-degree polynomial, so on and so forth. So that brings us to our example 8, where we're asked to sketch this straightforward cubic function. And then maybe I'll bring in a graph. So x-intercepts here, can very easily identify them. We have -2, 1, and 3. Nothing's being repeated. So you know straight off the bat, we're dealing with a cubic function. And nothing's negative either, so it's just going to be something like this. So we have -2, 1, and 3. Let's put in our y-intercept to just give us another point. Plug in 0 wherever you see x. So we have 2 times -1 times -3, which just gives you 6. So 0, 6. And then you're only asked to sketch it, so that's really all you need at this point.
Is multiplication or division? Or
What do you mean? Oh, it's multiplication. For finding your y-intercept? Yeah, multiplication, because the parentheses aren't being multiplied. Yeah, 2 times -1 is -2 times -3 is +6. Right, multiplication. And that's it. So that's your sketch. And then again, don't forget to write it out. X + 2, x - 1, x - 3.
How do you insert cubic function?
Because your exponents for each of these binomials are 1, which means we have x times x times x. Your highest degree is going to be x to the third. Yeah. Any other questions? All right. Let's look at this one. This one, we have a multiplicity that's taking place. And then we also have a little reflection. So as soon as you determine whether we have an odd degree or even degree polynomial, we look at that end behavior, and then we want to reflect it over that x-axis. But let's start off simple. Let's just look at our x-intercepts. We have our x is equal to -3. This is with a multiplicity of 2. And then we have x is equal to 5. So we're dealing with another cubic function. Your highest degree is 3. And then we also want to make note that because this is negative, we have reflect across x-axis. Let's also put in our y-intercept. Wherever you see an x, put in 0. So we have -2 times 3 squared times -5. -2 times 9 times -5 gives you +90. And cubic function, let's draw out regular x cubed. And then now let's draw out the reflection of it, because we're going to be looking at the reflection one instead, which tells us that our end behavior is as x goes to -infinity, y shoots up to +infinity. And then as x goes to +infinity, y shoots down to -infinity. So now we have all that we need in order to sketch this out. We're going to go ahead and plot in our x-intercepts. And then our y-intercept, I guess I'm going to go up by 10s, 10, 20, 30, 40, 60, 70, 80, 90. And at that -3, it's gonna bounce off the x-axis because we have that multiplicity of 2 there. So again, our end behavior is gonna look like what I have circled down in purple. So we're gonna end up with something like this. We have bounces off here. That's our first hump. And then this is our second hump. Again, sketching is nice because it doesn't have to be super accurate. And there we go. You're probably like, oh, but it looks a little different than this one. This is because your multiplicity at 0 is 3. So if you wanted to have distinct roots, it would look something more like this, which is exactly what we have here. Any questions? Good question. Because you're using your zero product property. So you take this binomial and you set it equal to 0, which means to solve for x, you have to add 5 to both sides. That's why the signs are opposite. Yeah. All right. Let's look at another example together, where now we have a quartic function, and that just simply means that our highest degree is 4, which means we have 4 minus 1, aka 3 humps, our W-looking graph. But it's negative So this is a version of x to the fourth, whereas negative x to the fourth, it's going to be reflected across our x-axis. It's going to look something like that. And that will very clearly give you your end behaviors for this function. So as x shoots to negative infinity, y shoots to negative infinity. As x shoots to positive infinity, y continues to shoot to negative infinity. Right. Now they give us the graph in our standard polynomial form, but I mean, we can clearly identify our y-intercept here. However, we're going to have to do some factoring in order to help us with finding our x-intercepts. So let's just very easily calculate our y-intercept. That's just going to be 0, right? You plug in 0 for all your x's and everything just shoots to 0. So your y-intercept is 0, which as a coordinate point, it's just 0, 0. But your x-intercept, we want to do some factoring. And lucky for us, we can pull out a greatest common factor from each of these terms. What can we pull out? Yeah, exactly. We can pull out an x squared. And when we do that, we're left with negative 2x squared minus x, bless you, plus 3. And now from here, we can, actually what I might do, because I don't like having this negative inside for that leading coefficient. So I'm actually going to pull out a negative x squared so that inside the parentheses, it's going to be 2x squared and then plus x and then minus 3. You don't have to. I just personally think it's easier to factor when you do.
So you like the AC method,
What?
you don't like the AC method factor out.
We don't like the what?
AC.
Oh, the AC method. We can use the AC method here. That's actually exactly where I'm going to get to for this next point. So what we have inside here is that 2, which is greater than 1. So let's utilize our AC method. Our A is 2, our C is negative 3, so the product is negative 6. And then our B is 1. What are factor pairs of negative 6 that add to 1? Yeah, exactly. 3 and negative 2, right? So now we can utilize our factor by grouping. You keep the first term the same. So you have 2x squared minus 2x plus 3x minus 3. Just manipulating this. I put the 2 first instead of the 3 because we can clearly see we can factor that. And then we are going to pull out a GCF for those first 2 terms. We can pull out a 2x. That way we're left with just x minus 1. Whereas those last 2 terms, we have, 3 we can pull out. And then we're left with x minus 1. And if you did it correctly, what you have in parentheses should be exactly the same, which it is. And so we can pull that out so that it is fully factored into our x minus 1, and then we have 2x plus 3. Yeah. And then all the way on the outside, you don't want to forget the whole negative x squared. So now that it's factored quite nicely, you can very clearly see what your x-intercepts are. We have some multiplicities that take place, right? That negative x squared gives us a 0 root with multiplicity of 2. So x equals 0 with a multiplicity of 2. And then we have a x equals 1. And then we have this 2x plus 3. If we set that equal to 0, ends up being fractional. You get negative 3 over 2, which is smaller than all of the others. So I'm going to put it first so that it's in ascending order. And so now we have everything we need in order to sketch out our graph. I'm just going to shrink this so that we have some more space. And then I'll put the graph right below. So let's plot some points. Our y-intercept we have over here, which happens to also be an x-intercept. And then we have our negative 3/2, aka just 1.5, negative 1.5. And then we have 1. And the multiplicity is going to be at that 0. So it's going to have a bounce off over there. And then the sketch is going to look like what we have over here in orange. So it's going to look something like this. Ugh, not drawing it well. There. Good enough. And then don't forget to write your function. That's it. Any questions? Yeah. You got that because it was x squared. So think about it as like x times x. So this one we have 0, and then this one we have 0. Yeah, that 2 in the exponent tells you how much that root is being repeated. So we become very used to having a binomial being raised to a certain exponent. So you're like, oh, multiplicity of 2 here at negative 3. But this was the first time where we saw it where it's just a monomial being raised to an exponent. That's why if you have like x to the third, you have a root at 0, but it's being repeated 3 times. And that's the common graph we always look back to, right? This is at that 0, it's crossing through and you have a multiplicity at 3. But any other cubic function that has distinct roots, it doesn't really look like this because that's where the repeated takes place. It looks something more like this, which is what we have in this example. Yeah. Does that make more sense? Yeah, okay, cool. All right. We're finally on to our last objective for today, which is using the intermediate value theorem. Very, very important theorem. And so I'll actually read this one too. Some people abbreviate it as IVT. So I'll put that in parentheses. But our intermediate value theorem for polynomial functions states that if p of x is a polynomial function and we have p of a and p of b be opposite signs, so like this is evaluated at, I don't know, -10, and this is evaluated at +20, then this theorem tells us that there exists at least one value c between our a and b x values for which p of c is equal to 0. Sounds a little bit confusing, but in short, what does that mean? That just means when your function changes from a negative y value to a positive y value, it must cross the x-axis. And I think there's a typo here. This wasn't finished. So it must cross the x-axis. And so we really have that visual being displayed here. Our p of a is a negative y value. Our p of b is a positive y value. And because we're dealing with polynomial functions that are continuous and smooth, we know that there will be no breaks from our a to b. And so it must cross over that x-axis. And you would yield a 0 at this value c that we labeled over here. Right. And so this really does help us out when we are given a polynomial and maybe we know one root, but we don't know another one. Or maybe we're asked, okay, can you prove that you have two real roots between this interval for the specific function? And if you know clearly, oh, 2 is a root, I can utilize my long division to simplify the polynomial a bit more and then utilize my intermediate value theorem to prove that we must also have another root between these two numbers because it goes from negative to positive. And then you have your proof. So we're going to be doing something like that in a moment. Actually doing it for this problem. And this problem, I kind of wish they gave us this example after we learned about dividing polynomials utilizing long division and synthetic division, just because you sort of need to do that in order to solve this problem. So I'll help you out a bit with this, but we'll do a lot more practice in our next section dealing with long division and synthetic division. So for this example, this is our last example for our 5.2 and 5.3. We're given our function x to the third minus 5x squared plus 3x plus 6. And we want to show that it has at least two real zeros between x equals 1 and x equals 4. And so first, we would need to see if we can find a factor. And you're probably asking yourself, oh my gosh, we're dealing with this cubic function, which I don't think is very easily factorable. The first notion that you might do is you might look at the first two terms and be like, oh, we have a greatest common factor here. We can pull out x squared. And when we do, we're left with x minus 5. And then if you look at the last two terms, we can pull out a greatest common factor of 3. And when we do that, we have an x plus 2. But then you really can't go too many places with that. So what you have to end up doing, which we'll learn about in the next few lessons, you're going to learn about P's and Q's, which we just denote these variables. It could be whichever letters you want. But these letters stand for our factors of our constant, which is your P's, and our leading coefficient. Which is our Q. And so our P is 6 here. We want to look for factors of 6. So for P, we're looking for our factors of 6, which is 1, 2, 3, and 6. And you can utilize both the positive and negative versions. So we are going to indicate plus or minuses. Whereas our Q's, we're looking at factors of the leading coefficient is 1 here. So lucky for us, that's prime. I shouldn't say prime, it's unique. So we just have plus or minus 1. And then the relationship between your P and Q is your question? No. We're dividing the two by each other. So because it's plus or minus 1 here, we're essentially just looking at our P's. So potential factors of this polynomial are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Because we're dealing with a cubic function, one of these options have to work. And so that really narrows down your possibilities from an infinite number of numbers from negative infinity to infinity. But for this sole purpose, since you haven't learned this quite yet, and we will be really going into detail with this in our next lessons, I'm just going to tell you that our factor is, or one factor is 2. So x equals 2 is a factor of our P of x. So now knowing that, we can utilize long division or synthetic division in order to simplify this. And synthetic is actually much shorter, but I'm not going to do synthetic with you right now just because I want to teach you long division first, and then we'll go into synthetic. Long division, I think you'll understand it a little bit more at this point. So essentially what we're doing is we're taking this whole polynomial, x to the third minus 5x squared plus 3x plus 6, and we're dividing it by our factor, but we can't just divide it by 2, because how would we just divide it by 2? It wouldn't make sense. 2 is our factor, and our factor is always written in the form of x minus c. So we have x minus 2. That's what we're dividing it by. How many people, raise of hands, have dealt with long division before for polynomials? Okay, all right. So now at this stage, We start off with our x. X times what gives you x cubed? X squared, right? And we just keep going. X times what gives you negative 5x squared? Negative 5x. And then x times what gives you 3x? Plus 3. And now, what we want to do is we are going to, wait, did I do this wrong? Yeah, I did this wrong. You're only looking at the first term first, x squared, right? It's a process. So x times what gives you x cubed, x squared. Now what we do is we take the product of this and then we subtract it from our polynomial. So we have x squared times x gives you that x third, which will end up canceling out. And then negative 2 times x squared gives you negative 2x squared. So this is what you're subtracting. Very similar to long division when you're just dealing with numbers. This will cancel out. These two negatives turn this to a positive. So we have negative 5x squared plus 2x squared gives you a negative 3x squared. And then we're just going to bring the rest of the terms down. So we have our plus 3x plus 6. Now we continue the process. So x times what gives you negative 3x squared? We have negative 3x. Negative 3x times x gives you negative 3x squared. Negative 3x times negative 2 gives you a positive 6x. And so what we have in this dark yellow, we're subtracting so that these two cancel out. 3x minus 6x gives you negative 3x, and then we bring down the 6. Let's keep going. X times what gives you negative 3x? It's minus 3. Negative 3 times x gives you your negative 3x. Negative 3 times negative 2 gives you your plus 6. We're subtracting. Lucky for us, this cancels out, and so does this. So your remainder is 0. Which is amazing because then that indeed proves that x minus 2, aka 2, is indeed a factor of the polynomial based off of the definition that we covered over here. Our P of C is equal to 0. So if we plugged in 2 into our function, we would indeed get 0 out. And so, what was the importance of all of this? Well, now, instead of looking at x to the third minus 5x squared plus 3x plus 6, you can look at x minus 2 times x squared minus 3x minus 3, which is much simpler to look at. I'm just going to make it smaller so we have some more space. So we have, again, our p of x is equal to x to the third minus 5x squared plus 3x plus 6. This is simplified to x minus 2 in parentheses x squared minus 3x minus 3. Okay. Almost there. So we know for a fact that 2 is a factor that's one of the real zeros between x is equal to 1 and 4, right? Because 2 falls between 1 and 4 on a number line. But now we want to figure out, okay, is there another number, another real zero between this? And because we already know that we have that one between really 1 and 2, let's hone in on now, okay, is there any between 2 and 4? Specifically, any number greater than 2 and less than 4. And so how do we do that? That's where we want to utilize our intermediate value theorem. So we want to look at a potential real zero between 2 and 4. And so how can we do this? Well, we know that at 2 it's equal to 0. So why don't we look at P of 3 and P of 4? Just because those are whole numbers, they'll be easy to calculate. If we plug in 3 into our function, and it doesn't matter, you can use this one or this one, they're both the same. Might be easier to compute here. 3 minus 2 gives you 1. Yeah, it's much easier, right? Because that will just cancel. And then we have 3 squared, which is 9, minus 3 times 3, which is 9. Oh, that shoots to 0. Minus 3 gives you negative 3. So we have a negative value here, negative y value. Think intermediate value theorem. We need to have a negative, and then it needs to jump to a positive for us to prove that there's another real root crossing through that x-axis. So if this is positive, we're good. If it's not, then we can't prove that we have at least two real zeros. So now 4 minus 2 gives you 2. 4 squared is 16, minus 3 times 4, which is 12. So 16 minus 12 is 4. And then we have 4 minus 3, which is 1. What's 2 times 1? Is it positive or negative? Ooh. So by our intermediate value theorem, we have another real root between 3 and 4, between x is equal to 3 and 4. And that's it. We proved it. I'll shrink this and just put that final sentence in. I would say this is definitely one of the more challenging questions in this course. So if you half understood what I said, that's great. And then feel free to rewatch this part of the recording to get a stronger understanding. So therefore, we have shown that P of x has at least two real zeros between x equals 1 and x equals 4. We're done. Another way I would say you can go about it, I mean, it really does help knowing that 2 is a factor of this polynomial function, but you can also take a guess, right? Let's say you evaluated between x equals 1 and x is equal to 2.5, and then you used intermediate value theorem. It went from positive to negative from x equals 1 to 2.5, and then you did another one from x equals 3 to 4, just like we did here. Then you'd be like, oh, we have two changes. It went from positive to negative, and then over here it went from negative to positive. So we know that there is a real root between 1 and 2.5, which happens to be 2. And then we have another real root between 3 and 4. So therefore, we've shown that p of x has at least two real roots between 1 and 4. So, any questions on this one? I know this is a tough one. Yeah. All right. So that does conclude our section 5.2 and 5.3.